Okay, so what we are doing today is Unit 4, Learning Set 3. It's covering complex zeros and the fundamental theorem of algebra. So our objectives are we're going to use the conjugate pair theorem, find a polynomial function with specified zeros, and find the complex zeros of a polynomial function. So remember, complex zeros, they are of the form a plus bi, so they have our imaginary number in it if they are complex. Another thing to remember is that if it is a real zero or a real number, that is also considered a complex number, because real numbers, let's say these are real numbers like 2, 3, 8, they fall in the range of complex numbers, such as 3 plus 2i, 2i, 5i, I times the square root of 3. Those are all complex numbers. So remember, real numbers are a complex number. So the first thing I want to review is Descartes' rule of signs. And basically the way this works is the number of positive real zeros is equal to the number of variations of signs. So if we look below, and what we mean by variations of signs is this 4 is positive, so it changes to negative, so that's one variation. The negative changes to a positive, so that is a second variation. Positive, positive is not a variation because they're the same signs. And then we have another positive to negative, so this is 3 variations, and there's no other variations. So what this means is this could have 3 or 1 positive real zeros, okay? Because it always goes down by an even number. The second part of Descartes' rule is the number of negative real zeros is equal to the number of variations of the signs of f of negative x. So we would take our original equation, put in negative x for x, so then it would be 4 times negative x to the 5th minus 3 times negative x to the 4th plus 7 times negative x to the 3rd plus negative x squared minus 6 times negative x minus 1. And then we need to simplify this. So any negative number that is taken to an odd power is always going to be an odd answer. So this 4x to the 5th would actually change to a negative 4x to the 5th. Any negative number that is taken to an even power is always going to cancel out those negatives. So this negative 3 is going to remain the same because negative x to the 4th power is just positive x. So because this is going to say negative, it's going to change the 7 to a negative x to the 3rd. This is going to remain x squared. This negative is going to change the negative 6 to a positive 6x minus 1. So now we're going to do the same thing. We're going to count the variations. So there's no change in this first one. They're both negative. The second to the 3rd term are both negative, and we don't see a change until we go from the 3rd to the 4th term. We have a negative to a positive. There's not a change in x squared to 6x, and there is one more change here. So the number of negative zeros is going to be either 2 or 1. And remember, because this is a degree 5, there are at least 5 zeros. Okay. Okay, complex zeros. So remember, a complex zero is a number that is expressed as a plus bi, or bi, where a and b are real numbers, and I represents the imaginary unit. So remember, the imaginary unit states that I squared equals -1. So we know if I squared equals -1, if we take the square root of both sides, I is equal to the square root of -1. So remember that. So if we want to find all of the real zeros in the polynomial below, what we want to do is we can factor this, okay? So we can take and rewrite this as f of x equals, and we know the first one's x with -12. It's going to be x squared because this is to the fourth power and the middle one is squared. It's going to become x squared minus 6 times x squared plus 2. So from here, what we can do to find the real zeros is we can say x squared minus 6 equals 0. Move 6 over, and we have x squared equals 6. And then remember, when we take the square root of something, it becomes a plus or minus, because when we square it, regardless of if it's positive or negative, we're still going to get a positive number. So the answer is going to be x equals plus or minus the square root of 6. So that would be 1, 0. On the other side, we have x squared plus 2 equals 0. So we have x squared equals -2. We want to find the square root of both sides. So x equals the square root of -2. Now at this point, we have a negative in our radical, and we don't want that. So we could take and split this up into x squared equals -1 times the square root of -2, or the square root of +2. And we know from what we talked about up here that the square root of -1 is our imaginary number. So our answer for this part would be, we would change that square root of -1 to I and leave it as I square root of, it's supposed to be, I'm sorry, I forgot to put the plus or minus the square root of 2. So our zeros would be plus or minus the square root of 6 and plus or minus I square root of 2. And you might also keep in mind that this breaks out into the square root of 6, the negative square root of 6, and this one would break out into I square root of 2 and negative I square root of 2. So keep in mind, when it's plus or minus, it breaks it out into two separate numbers. So looking at another example, find all the zeros of the polynomial function below. So the first thing I would do here is I would factor out -2. And when you factor out -2, so this leaves me with x cubed. I factored out the negative, so it leaves me with a +8, so +8. Okay, and then also we can factor out x plus 2 using the rules we've known before, times x squared minus 2x plus 4. So in this case, you could also do synthetic division for this one. You could say for the x cubed plus 8, I want to try -2. Okay, and so x cubed would be 1,008. Factor it out. +4, -8, 0, and that would leave us with x squared minus 2x plus 4. So you can either use the rules that you learned in Algebra 2 to split out a trinomial, or you can use synthetic division to break it down. So at this point, then we can go back and figure out our factors. So I know this first one is x plus 2 equals 0, so x equals -2. So that's one of our zeros. So my zeros, one of them is 2, or I'm sorry, -2. The other thing on the other side, we can't factor this out evenly. So we want to use the quadratic formula. So remember, the quadratic formula is -b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so what we would do here is we know that a equals 1, b equals -2, and c equals 4. So plug in our quadratic formula. X equals -2 plus or minus the square root of -2 squared minus 4 times 1 times 4 divided by 2 times 1. We're going to simplify this 2 because negative negative is positive, and under our square root sign we end up with -12 when we do the calculation, divided by 2. So we want to simplify this more, and we know that we could have -1, and 12 can also be broken out into the square root of 4 times the square root of 3. So we end up with 2 plus or minus -1 becomes I. Square root of 4 is 2, and we left with the square root of 3 divided by 2. And we can simplify this even more because both sides of the equation on top are divisible by 2. So that would then become x equals 1 plus or minus I square root of 3. So our zeros end up being -2 from the first side. We have 1 plus the square root of 3, and we have 1 minus the square root of 3. Oops, I'm sorry, hold on. There should be an I in front of that square root of 3. So it should be 1 plus I times the square root of 3 and 1 minus I times the square root of 3.